Dear students, in the last class I had explained a new lesson, which is Newton's laws of motion, and let's learn more about this particular chapter. So I'm going to start with an illustration where, so we have a rocket and the countdown is on, and it's now 3 seconds, 2 seconds, and moment it's 1, again the fuel is get burnt, and there is the burnt fuel moves in the downward direction, whereas the rocket, it moves in the upward direction. That is, if I consider two bodies, one, the rocket, and the other is the fuel. Okay. Initially, both rocket and fuel, they are at rest. So what is the momentum of the rocket and the fuel? Total momentum of the rocket and the fuel, that is 0, because both are at rest. How do we calculate the momentum? Momentum is always a product of the mass and the velocity. Mass of the rocket, velocity of the rocket is 0, that's why momentum is 0. Fuel is yet to burn, so again it is not moving, it is at rest, therefore its momentum is 0. That's why total momentum is 0. But once the rocket starts moving there in the upward direction, why it moves upward? Because the burnt fuel moves, you can see that, in the downward direction. So one has momentum in the upward direction, other has momentum in the downward direction. So one momentum is taken as positive, other momentum is taken as negative. So when you add this, you will get that also equal to 0. That means total momentum before launching is equal to the total momentum after launching the rocket, and that is called the law of conservation of momentum. So what is the statement? So in a closed system, the total linear momentum of the system remains constant. In a total system, in a closed system, the total linear momentum of the system remains constant. So this is a good illustration for the law of conservation of momentum. So in one more illustration where, so this is a baseball, the ball moves in one direction, it has certain momentum before hitting, then the baseball bat moves again in one more direction, it has a momentum, and once the ball strikes the bat, the ball moves in one direction, and the bat at that instant slightly moves backward at the instant, when it is hit, not after hitting. At the instant when it is hit, the bat slightly moves backward. You can see that at the instant when it is hit. Okay. So here, the total momentum before hitting the ball is equal to the total momentum after hitting the ball. So same is valid even in the case of the ball hitting a cricket bat as well. Then if you take one more illustration where a person is in a boat. So this is the boat and the person is here. The boat is at rest, the person is at rest. So the total momentum before jumping out of the boat is 0. But once the person jumps out of the boat slightly moves backward. So his momentum is positive, whereas the momentum of the boat is negative because it's moving backward. So the net momentum becomes equal to 0. So total momentum before jumping out of the boat is equal to the total momentum after jumping. So basically here what we try to relate here is the total momentum of the system is always conserved. So that's why momentum is a conserved physical quantity. And we have a proof for this law of conservation of momentum, and that is what we are going to derive right now. Right. So what we are trying to prove here is the law of conservation of the linear momentum. So first I'm going to consider a body A moving in a particular direction, and it has momentum P suffix A. There is another body B moving in the same direction with a momentum PB. So this is the momentum of A and this is the momentum of B. And I'm going to assume that this momentum of A is more than that of the momentum of B, and the velocity of this A also greater than that of B, and since its velocity is greater, at one instant it will go and collide. So there is a collision takes place between the two, and when they collide, they exert force on one another. So the force exerted by A on B, I'm going to write it as F1. Force exerted by B on A, I'm going to write it as F2. So these two forces are equal and opposite. They obey Newton's third law of motion. And after they collide each other, there is a change in momentum takes place. So therefore, the momentum of A after the collision is PA dash. What is PA? Momentum of A before the collision. This is momentum after the collision. So again, the momentum of B also changes to PB dash. PB is the momentum of B before the collision. PB dash is the momentum of B after the collision. So during this collision, let us assume that they exert force or they are in contact for a duration of delta t. So delta t is the time of impact or time of collision. We can always find the force. So what is the first force? F1. Force exerted by A on B, and force is always the rate of change of momentum. So how to find the rate of change of momentum? So F1 is equal to change in momentum, that is a PB dash minus PB. PB dash minus PB. Now this is the change in momentum. Rate of change of momentum means I have to divide by delta t. So this is one of the equation. And this is basically considered as the action. So what is action here? Force exerted by the first body on the second, which is F1 is equal to PB dash minus PB by delta t. And the reaction is B exerts force on A. So therefore, F2 is equal to the change in momentum of A now. So which is PA dash minus PA divided by delta t. So this is the second equation and this is the reaction. So what is the action? Action is the force exerted by A on B, and the reaction is force exerted by B on A. And according to Newton's third law, action and reactions are equal and opposite. So F1 is equal to minus F2. So what is F1? F1 is this PB dash minus PB divided by delta t is equal to this minus of PA dash minus PA divided by delta t. This delta t will get cancelled here. So therefore PB dash minus PB is equal to minus of PA dash, open the bracket, minus of minus becomes plus PA. And if I rearrange here, so this minus PA dash, I'll bring to the left hand side here. So PA dash plus PB dash is equal to PA plus PB. Correct? So we can even write, just interchange, write this on the left, write this on the left here. Sorry, write this on the left, write this on the right. So PA plus PB is equal to PA dash plus PB dash. So look at this sum. This is nothing but sum of the momentum before the collision, PA plus PB. This is sum of the momentum after the collision, and that is what the law of conservation is all about. What is law of conservation? Total momentum of the system remains constant. Therefore, we have proved that the total linear momentum before the collision is equal to the total linear momentum after the collision. The same thing we can even write in this format. If u1 is the initial velocity of the first, and if u2 is the initial velocity of the second, having mass m1 and m2, then this is m1 u1. m1 u1 is the momentum. m2 u2, so plus m2 u2 is equal to, after the collision, let their mass will remain the same, velocity changes to v1. Mass is m2, velocity changes to v2. So we can write that's equal to m1 v1 plus m2 v2. So this is how we can use this equation. So this is also an alternative equation to relate the velocities before the collision and velocities after the collision. So what is the equation? m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Where what is m1 and m2? Masses of the two bodies. What is v1 and v2? Sorry, u1 and u2. They are initial velocities before the collision. What is the v1 and v2? Final velocities after the collision. So this is the proof. It's a important 5 marks question, and they'll ask proof the law of conservation of linear momentum in the case of two bodies are colliding each other. So you need to derive this particular equation. So let's solve a numerical based on the previous exam question. Statement is here. A body of mass 20 kg. So first body, I'm going to write like this. First body, mass is given 20 kg. Moving with a velocity of 10 meter per second. So its initial velocity is given 10 meter per second. Collides with another body. So this is the second body. Mass is 40 kg. 40 kg. Moving with the velocity of 5 meter per second along the same direction. So u2 is given 5 meter per second along the same direction. Now first option, if both the bodies stick together, so first option, that means sticking together means they move together, with the same velocities. Okay, that means v1 is equal to v2 is equal to v. If both the bodies stick together after the collision, find their common velocity. Find their common velocity. So I'm going to use the formula m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is the formula. So m1 is a 20 and u1 is a 10 plus m2 is a 40, u2 is 5. So here v1 and v2 are equal, which is v. It's a common for both. So write m1 plus m2, which is 20 plus 40, that is 60 into v, which is common. So this is 200 here. This is another 200. That's equal to 60 into v. So 400 is equal to 60 v. So v is equal to 400 by 60. 0 will get cancelled. That is same as 20 by 3. And 20 by 3 is 6.66. We'll get recurring here. So 667. We are finding velocity, so that's why it is meter per second. So this is the first option. The second option that is asked, after the collision, if the heavier body moves with a velocity 8 meter per second in the same direction, so the data is the same, okay, that is m1 is 20 kg and u1 is 10 meter per second and m2 is 40 kg and u2 is 5 meter per second, and it's given that the heavier body moves with a velocity of 8 meter per second. Heavier is this is heavier. Moves with a velocity, that velocity is given, v2 is given, with a velocity 8 meter per second, 8 meter per second in the same direction. Then find the velocity and direction of the lighter body. We have to find the value of v1. Okay. So let me use this space here. Formula remains the same. M1U1 plus M2U2 is equal to M1V1 plus M2V2. The value of M1 is a 20. 20 into the value of U1 is a 10 plus the value of M2 is a 40 into U2 is a 5. That's equal to M1 is a 20 into V1 we need to calculate plus the value of M2 is a 40 into the value of V2 is a 8. So this is a 200. So this is 200. That's equal to 20V plus this is 8 4 32 320. So this is 400 is equal to 20V plus 320. 400 minus 320 is 80 is equal to 20V and V is equal to 80 by 20. So which is 4 meter per second. That is V, this is V1. Okay. So we have found the velocity and they have also asked the direction. So 4 meter per second, since it is positive in the same direction as that of second body. So second body moves, in the same direction. So even the value V1 what we are getting is a positive. So which means it is same as that of the second body. In case if you get V1 as negative, then it will move in a direction opposite to that of the second body. Okay. So this is how you have to solve the problem, and important problem from the examination. So now refer this diagram illustration where, so we have a block, this is a block, and hope you get to see there is a spring here. The block is moving closer to the spring, and during this there is a compression in the spring, and now there is a elongation in the spring. So during the compression, the spring is get compressed like this, in this direction. Okay. During the compression, the spring is get compressed like this, to the left. So this is the compression. And when it is get compressed, let delta x be the change in the length of the spring. See, because when it get compressed, its length decreases, right? And I'm going to consider that as delta x. And when the spring is get compressed to the left, a force is developed in the spring in the opposite direction, and that is called the spring force. So spring force and the change in the length are always opposite. So this is during the compression. So now the spring is get compressed. Now see, when the spring is get elongated, the change in the length will be to the right, and a spring force is developed within the spring in a direction opposite to this. So therefore in this case the spring force will be opposite to the change in the length of the spring. So when the spring is compressed like this, it is in this direction, correct, to the left. So spring force is to the right. When the spring is get elongated, which is to the right, the spring forces get compressed, the spring force acts in a direction opposite to that of the elongation. So that these are related, as like this, Fs is equal to, since the directions are opposite, it's a minus k into delta x. So this is the formula for the spring force. So what is the spring force? Force which is developed within the spring during the elongation or compression is called as the spring force. Okay, and K is called spring constant. K is called spring constant. We can find the unit as well as the dimensional formula of the spring constant. K is equal to Fs by delta x. I am going to take the magnitude, I will not take the sign. Now, force, spring force, it is measured in Newton. Change in the length is in meters. So, therefore, Newton per meter is the unit of spring constant. If the spring constant is less, then we call that as, soft spring. If the spring constant is more, we call it as a hard spring or a stiff spring. Soft spring means smaller value of K, hard spring means a larger value of K. Springs having smaller value of K, we get to see inside pen where they use a small spring for the movement of the refill. That is a soft spring, correct. Whereas the hard springs are used, in a vehicle as a shock absorber, which is very hard. So those are springs having higher value of K. And when we write Newton per meter, I can write the dimensional formula, force, which is ml T minus 2 by meter, which is L. So this L will cancel and we'll get m T to the power minus 2. So that's the dimensional formula of the spring constant. So spring force and spring constant are related using Fs is equal to minus K in delta x. K is the spring constant. Minus sign indicates that the change in the length of the spring and the force are always opposite to each other, where delta x is either the elongation or the compression of the spring. So this is about the spring force, and the remaining topic of this particular chapter I am going to continue in my next class.